Have you ever just, stopped and really looked up, like properly looked at that incredible blue sky on a clear day,
Hmm.
or watched those huge, fluffy white clouds drift past and thought, hang on, why those colors? It's something we see literally every day.
Yeah, we take it for granted, don't we?
Or we really do. But there's some amazing, elegant science going on up there, painting our world. So today we're doing a deep dive into the physics behind it all.
We're going to unpack why the sky is blue, why clouds are white
Yeah.
and sometimes gray,
Exactly. Using some great sources to figure out what's creating the blues, the whites, and, well, everything in between.
and what's really cool, I think, is how fairly simple principles, things about light and tiny particles, create these huge, beautiful effects we see all the time.
Okay, I'm ready. Let's decode this everyday mystery. So where do we start? It has to be the sunlight itself, right?
Absolutely. That's the source. It looks white or maybe yellowish to us.
But it's not just white light, is it? Our sources say it's actually a mix of loads of different colors all bundled together.
That's spot on. Think of a rainbow or light through a prism. You get red, orange, yellow, green, blue, indigo, violet, the whole spectrum. It's
Yeah.
all in there in that sunlight.
Right.
And the key thing here, the concept we really need to grasp, is wavelength. Each of those colors has a different wavelength.
Okay, wavelength, like waves in the sea.
Kind of, yeah. You can think of it like that. Red light has the longest wavelength, its waves are sort of stretched out. Violet light, on the other end, has the shortest wavelength, much more compressed, faster waves.
Gotcha. Long waves for red, short waves for violet and blue.
Exactly. And this difference in wavelength is absolutely crucial. It determines how the light interacts with, well, with our atmosphere.
Okay, so different wavelengths behave differently when they hit the air. That sets us up perfectly for the big one. Why is the sky blue? What happens when that sunlight hits the atmosphere?
Right. So sunlight comes streaming in and it immediately starts bumping into stuff. Mostly it's hitting the tiny molecules that make up the nitrogen and oxygen primarily.
The air itself.
The air itself. Now here's the critical part linked to wavelength. These air molecules, nitrogen and oxygen, are really small. Much, much smaller than the wavelength of the visible light hitting them.
Okay, tiny molecules, bigger light waves.
And when light hits particles that small, it scatters. It basically gets bounced off in all directions.
Ah, okay, so it's not absorbed, it's just redirected.
Precisely. Redirected. But, and here's the kicker, not all colors scatter equally when hitting these tiny molecules. Because blue and violet light have shorter wavelengths.
So ones with the compressed waves.
Yes. Those shorter waves are much more likely to interact with and get scattered by the tiny air molecules compared to the longer wavelengths like red or orange.
Interesting.
This specific effect, light scattering off particles much smaller than its wavelength, has a name. It's called Rayleigh scattering, named after Lord Rayleigh, who figured it out.
Rayleigh scattering. Okay, so blue light gets scattered way more than red light by the air. How does that make the whole sky look blue?
Well, think about it. That blue light is being scattered everywhere, constantly, by molecules all throughout the atmosphere, up, down, sideways.
So no matter where I look, some of that scattered blue light is heading towards my eyes.
Exactly. It's reaching your eyes from every direction, from all over the sky. It sort of fills your vision. That constant stream of scattered blue light makes the entire daytime sky appear blue.
Wow, it's like the atmosphere itself is glowing blue in a way.
That's a good way to put it. It's diffusing that blue light everywhere.
That's genuinely amazing. But then, okay, what about sunsets and sunrises? If blue light scattering dominates, why do we get those incredible reds and oranges then? That seems like the opposite effect.
Yeah, it's a great question, and it builds directly on the Rayleigh scattering idea. It's all about the angle of the sun.
Oh, in the sky, right.
Right. At sunrise and sunset, the sun is very low on the horizon. So the sunlight reaching you has to travel through much more atmosphere than when the sun is high overhead at noon.
Ah, longer journey through the air.
A much longer journey. And along that longer path, there's more air, more molecules, more opportunity for scattering. So most of the shorter wavelengths, the blues and even the greens, get scattered away before the light gets anywhere near you.
They get filtered out, essentially, scattered off sideways so much they don't make it straight to my eyes.
Pretty much. They're scattered so effectively over that long distance that they're largely removed from the direct beam of sunlight reaching you. What's left?
The longer wavelengths, the reds and oranges.
Bingo. The reds and oranges, with their longer wavelengths, are less likely to be scattered away. They make it through that thicker slice of atmosphere more successfully. So the light that finally reaches your eyes is heavily biased towards those warm colors.
That makes perfect sense. It's not adding red, it's taking away the blue. Simple, but really elegant. Okay, let's switch gears. Clouds. They're floating in that same blue sky, but they're usually bright white. Why aren't they blue too?
Good question. This brings in a different type of scattering. The key difference is what clouds are made of.
Water droplets, right? Or ice crystals.
Exactly. Tiny droplets of water or little crystals of ice. And the crucial point is that these droplets and crystals are much bigger than the individual air molecules we were talking about for Rayleigh scattering. Way bigger.
Okay, so particle size is the big difference here. Bigger particles in clouds, tiny molecules in the clear air.
Precisely. And when sunlight hits these much larger particles that are similar in size to, or even larger than, the wavelengths of light, a different process takes over. It's called me-scattering.
Me scattering. Okay, new term.
Okay.
How is that different from Rayleigh scattering?
Well, me-scattering is much less picky about wavelength. When light hits these larger cloud droplets, it scatters all the colors of visible light, red, green, blue, everything more or less equally in all directions.
So it doesn't preferentially scatter the blue like the tiny air molecules do. It just scatters everything together.
Exactly. It's an equal opportunity scatterer, you could say. All colors get bounced around pretty evenly.
Okay, so if all the colors red, orange, yellow, green, blue, violet are scattered equally, and then they all mix back together when they reach our eyes.
What color do you get when you mix all the colors of light back together?
White.
White light. That's why clouds typically look white. It's the combined scattering of all the colors from the sunlight hitting those larger water droplets.
That is so neat. Same sunlight, different particle size, totally different color effect. Rayleigh for the blue sky, Maya for the white clouds.
You got it. And understanding me-scattering also helps us figure out that last piece. Why clouds sometimes turn gray or dark.
Great, the gloomy-looking storm clouds, they're definitely not white. What's happening there? Is it still me scattering?
It is, but something else is happening too. It mostly comes down to the cloud's thickness or its density, how much water it's holding.
Okay.
When a cloud gets really thick, really deep and packed with water droplets or ice crystals, it starts to block the sunlight.
So it's like there's just so much stuff in the way.
Basically, yes. There are so many droplets that a lot of the sunlight gets scattered multiple times within the cloud or absorbed, and less of it makes it all the way through to the bottom or gets scattered out towards your eyes from the base.
So less light is escaping the cloud in my direction.
Exactly. Less light reaches you from those really thick, dense parts. And when less light reaches your eyes from an area, it appears.
Darker, gray, or even black if it's really thick.
Precisely. So a cloud's apparent color, from bright white to deep gray, is largely determined by how thick it is and how much light it manages to scatter towards you versus how much it blocks or absorbs.
Air molecules scatter short wavelength blue light more effectively. That's Rayleigh scattering.
Mm-hmm.
Clouds are white because larger water droplets scatter all colors of light pretty much equally. That's me scattering, and they mix back to white.
Correct.
And gray clouds are gray simply because they're thick enough to block a lot of the sunlight from getting through to our eyes.
That's the essence of it. Simple concepts, really. But they create the entire canvas above us.
It really makes you look up differently, doesn't it? Knowing what's going on. Next time you're outside, you'll actually see the physics happening.
Hopefully. It adds another layer of appreciation, I think.
Definitely. And it makes you wonder, doesn't it? You know, our atmosphere has this specific mix of gases, these specific conditions. How finely tuned is this balance that gives us this vivid blue and white? What if our atmosphere was slightly different? Thicker, thinner, different gases?
How different would our world look? It's a fascinating thought. It highlights how unique, maybe even fragile, the conditions are that create this everyday beauty we often just ignore.
A good reminder to just look up sometimes. Really look.